Hello. The today's topic is the definite integral. So let's write it. So we call it definite integral. Definite integral. So in Thomas' book, this is section 5.3, and in the Stewart book, this is section 5.2. Okay. So what's the definite integral? So let's start with the notation first. So we have something, so we can write it like that. So we have the integral sign, we have what we call the lower limit and the upper limit and the integrand, and then we have dx. So that is the notation of a definite integral. So this is what we call the definite integral. Definite integral. So there are a few things that we need to remember. So we have what we call the lower limit, and then we have what we call the upper limit, upper limit, and then we have the integrand. Yeah, so so these are the few things that we need to remember. And then so other things, what we call the process of calculating an integral. An integral is called, the process of calculating an integral is called integration. So integration means you add, simply like meaning that you add, you integrate, you add. But it's kind of add, why it is an add? Remember, so let's try to go back to what we call the Riemann sum that you learn in Calc 1. Riemann sum. So let's have another look at it. So what we did, so you have a graph. So let's say this is your graph, and then so what we did, we try to find the area below the graph. Okay, that's the whole point. We try to find this area. So what we did, we're gonna split this into rectangles. Okay, so we split this into rectangles. If you can find equal rectangle, that's much easier, but that's not a must. You can just find any rectangle with any gap, but to make our life easier, we just try to divide into rectangles equal size. So let's say you start with a and b. You can see those a and b, those are the limits of the integral ab. It's kind of interesting. Okay, and then you have function. So function is y equal fx. That's your function. So what you did, you're gonna kind of split this into small rectangles. Now there's a question: what are you gonna do? So you have a lot of options. So what are the options? You can pick the left end-point, or you can pick the right end-point. So what are the options? So you can pick. Let me write the options. So the options are pick the left end-point, so you're going to pick this corner as the typical value, or you can pick the right endpoint, or you can pick the middle point, or what we call the midpoint. Okay, so you're going to pick the value at the midpoint, each midpoint, or pretty much you can pick any point. So you have like a lot of options. You can pick the left hand point, right hand point, midpoint, any point. So for example, let's say you pick the right hand point. So if you pick the Actually, I'm going to pick the left endpoint because you can see some interesting results if I do that. So what I'm going to do, I'm going to pick always the value at the left endpoint as the typical value. So I'm going to go to this interval. So I'm going to pick the value at the left endpoint. So this is the typical value. So I'm going to consider that's the value for the whole interval. So that means I'm going to approximate the area under the curve by this value, the area of this rectangle. Okay. Now what I did, I picked the left endpoint. So do the same thing. If you go to the next interval, that's the left endpoint here. So I'm going to pick this value as the typical value. So this is the rectangle you get. Okay. So you can see that in the previous one you get a underestimate, this time you get a overestimate. So you know what's going to happen, you know, you get underestimate, overestimate, they kind of cancel each other. Not really, but you know, you can see that in this case you can cover so if I draw something like this, you can see you can fill this one here. So it's kind of gonna fill that. Okay, not really, but it's very close, very close. So we just keep doing it. So you're gonna pick the left endpoint every time. So I'm gonna put the left endpoint here again. So this is the rectangle you get. Pick the left endpoint. This is the rectangle you get. And you pick the left endpoint. That's the rectangle you get. Okay. So this is what you did in Calc 1. So I'm just repeating it just to tell you because this is where we can start. So so I'm gonna pick the left endpoint. Now what I'm gonna do? I'm gonna evaluate these areas. Okay. I'm gonna these areas. So the other question, you need to like kind of mark them, you know, like, you know, we need to find the values of the function at these points. You need to know what are those values. So so you can say I mean it's just the notation is simply up to you. What we normally do is I'm going to start with the first value. We normally call this x0 value, and then we're going to go to the next one. That's I'm going to call it x1 value, and then x2 value, x3, x4. In this case you get x5. So x5 is the last value, x5. So how many intervals you divide, it's just up to you. Okay, so more the better, more the better. Okay, so that's important, more the better. Okay, good. So let's look at some notations that we use in Calc 1. So we need a kind of idea, like, you know, so what is the gap? Let's say you divide into equal, so equal gaps. This one gap I'm going to call it, so one such gap I'm going to call it delta x. So that's the gap, delta x. So what is the gap in this case? It is b minus a, that's the whole gap, divided by number of intervals you cut. So in general you're going to say you're going to cut into n intervals. So in this case n equal 1 2 3 4 5, so n equal 5. Okay, so n equal 5 for this problem, but this is a kind of formula, the gap of one such interval. Now what we're trying to do, we need to find a formula for each x value. Okay, so we have x0. How to get the x1? X1 is what? X1 is simply x0 plus one such gap, right? x0 plus one such gap. What is x2? x2 is x0 plus 2 such gap. So like that. So that means if I need a formula for ith one, it is x0 plus I many gaps. So that is the formula. You add I many gaps to the first one. Okay, so xi equal x0 plus I many gaps. Good. Now what you're gonna do? So you pick whether you want the left endpoint, right endpoint. So let's say you pick the left endpoint, then you're going to calculate the function at the left endpoint. Okay, and once you calculate the function at the left endpoint, you can find a area of a typical rectangle. For example, if you calculate the area of this rectangle, what do you get? So the value at the so we're going to say area. So I'm going to say delta A. Okay, just the area of that one rectangle. Delta means small. Okay, when you say delta, that means that small. So delta A of that area. So what is that? It is the height is what? So it is the height times the width. So height times the width. So what's the height? Height is the function value at x3. You can see So that's the value. So function value at x3, that's the height. So that means f x3. And what's the width? Delta x, because we assume that they are equal. So that means that is the approximate, that's the area of the rectangle, that's the approximate value under the curve. Now what we're gonna do, we're gonna add all of them. We can add all of them. Okay, so so that means, and then once you add all of them, that's what you call the Riemann sum. Okay, that's what you did before. That's what you call the Riemann sum. So that means that sum. So so you can say so it's a it's a sigma. Sigma means you're going to add all of them. You're going to start with the first area that go with x0, and then you're going to add all of them. Let's say you're going to, in general, you're going to divide this into n many parts. So that's the nth part. So there are n many parts. And then what do you want to do? You want to find the area of one such rectangle. One such rectangle is simply f. So if I go with the ith one, it is f xi delta x. So that is the area of one such rectangle. So the ith one, okay, ith rectangle, the area of the ith rectangle. So the area of the ith rectangle. Okay, so area of the ith rectangle. And then what do you want to do now? So this is the area of one such one, but you want to make sure that the array is small. How you make the array small? You're going to make n larger and larger and larger. When you make n larger and larger, this array getting smaller and smaller and smaller. So what you normally do is you're going to send the limit when n goes to infinity. N goes to infinity. So, and also you can show that it doesn't really matter what point you're going to pick. You can pick either left end point, or you can pick either right end point, you can pick the middle point, you can simply pretty much pick any point. So just to mean that I'm going to star here, just to mean that you can pretty much pick any point at the end. When you take the limit, it doesn't really matter. Okay, so any point in the ith interval, inside the ith interval. Okay, it can be corners or it can be something in the middle. Okay, so it doesn't really matter. So that's why we say that's just put a star, just to mean that you pick any point you like. Okay, it can be left end point, right end point, middle point, or any point. Okay, and then so you can pick any point, it doesn't really matter. But when you have like a few numbers, you know, like 5-6 points, you might see a difference because you have a lot of error. But once you have large and larger numbers, you don't really see a difference when you pick different numbers. Okay, you can make it really small. But now what's going to happen? This sum, when you send n to infinity, this is what we call the Riemann sum. And this Riemann sum you're going to define by a new notation, that is the integral. We're going to call this sum the integral of the function fx and dx. So we write it like that. Dx corresponds to the delta x part, fx is the f xi star. So you can see they simply correspond, and the sigma means the sum. So like in early days, they write like this big, it's like that, but we kind of make it stylish, and then now we write it like that. Okay, so still it is the sigma, so it's over the sum. Okay, the integral sign means the sum, but we write it like this now. Okay, so a little bit stylish. Okay, so so this is the idea, and then with this sum, this whatever the value you get, and that's now going to be, because when you get n is large and large and larger, that means you're going to cut more and more and more into pieces. You simply ignore the error because the error getting smaller and smaller and smaller, so it's going to go away. You pretty much get the area below the curve. Okay, so that's the kind of idea. So that means this we can use as a kind of formula. Okay, so and that answer now we call the integral. Okay, the definite integral. So you know the numbers, there's a number a and b, so this is what we call the definite integral or the Riemann sum. Okay, so this is the Riemann sum. So in the Riemann sum, what you do is you send the n to infinity. So when you send n to infinity in the Riemann sum, you call that is the definite integral. So now you can see that the definite integral is a number. Okay, definite integral is a number. So So this is the kind of basic idea, and you can see that the rest of the course simply depend on this. So make sure like you understand this slide completely. So this is here we talk about like all the ideas. So we're gonna do like maybe one problem just to understand, but in the homework I'm gonna actually this is something we didn't calc one. So here this is just a repetition, okay? Because because we need to see the connection between what you did there and how we can derive. So then we so you look at the Riemann sum and send n to infinity. That's you gonna represent as an integral, and then we just call it the integral a to b fx dx. Okay, integrate means you add sum. Okay, so that's the kind of idea. Okay, so good. Now so let's try to understand a few things. So what are the few things? So you can see the definite integral, which is a number. Okay, that's one thing. Okay, so so the first thing is we can call it the definite integral, definite integral a to b fx dx is a number. Okay, that's very important. So you get a number. What's the number? Represent. This number is the area. All right, area. I'm gonna call it like that because there are some weird things can happen. So why is that? So one thing is like, let's look at this situation. So this what we normally call signed area. Okay, so the area has a sign. For example, let's look at the sine graph. Okay, so if you look at the or let's look at this cosine graph. That's much better. If you look at the cosine graph from 0 to pi, so this is what you get. Right, that's a cosine. Now the thing is that let's say you integrate this, okay, from 0 to pi cosine x dx. What do you get? What do you think you get? So let's try to understand what's going on here. So we do the same thing. We're going to strip this into small rectangles. Let's say you get a typical rectangle here. And then you can see that the height is positive now. Okay, so this height has a positive value. Okay, when you add, so so I'm going to call x1 value here. So you say fx1, which is a positive value. All right, but you have to do the same thing with the other one, because you try to find the area. So when you find the area become positive, because the gap is still the same. So delta x, that's a positive number. So delta x, we assume that is always positive. This is always positive. But the height this time is positive, so you get a positive area for the first part. What about this one? If you do the same thing with this rectangle, now so I'm going to call this corresponding x1 is x2. What happened to fx2? Fx2 is negative, so you get a negative area. Okay, but you know that if you look at the cosine graph, this the top part and the bottom part are symmetric. They are same. They are the same. So that means if you add all those area from the top and the bottom, what's going to happen? You get a positive area here, plus a. I'm going to call it plus a. That's the area of the first part, and then you get a exactly same one, but with the negative sign, because the heights are negative now. So you get negative area. So what's going to happen? They cancel each other and get 0. And you can show that that's the case, because you know the integrand. This is a simple antiderivative from what you learned in the last class. So so you can see that that's the case actually, because actually this is something we want to learn in the next section, but I'm going to do it right here just to tell you what we can expect in the next section. So the so we know the antiderivative. What's the antiderivative of cosine x? Antiderivative of cosine x is from the table sine x. Okay, that's antiderivative, and you can also add a plus c if you want. But in the next section we show that this antiderivative actually kind of give you the error until the x position, area until the x position, total area under the x position. But here we have two numbers, 0 and pi. So what do you want to do? You only need to find the area between 0 and pi. You don't need rest. So you have a 0 here, you have pi there. But this formula gonna give you the area up to x. Okay, area up to x. So that means if you want to get the area only between 0 and pi, what do you need to do? You want to find the area at the pi value. So you're going to find the area at pi. So sine pi plus c. So that's the area at pi. But you know that you only need the value between 0 and pi. So that means you need to subtract the value at 0. So let's subtract the value at 0. So sine 0 plus c. That's the value at, that's the area at 0. This is the area at pi. Alright, total area. So area at pi. This is the area at 0. Once you subtract the two areas, you're going to get the area between 0 and pi. Okay, so let's simplify. What is sine pi? How much sine pi? Sine pi is 0. So sine pi is 0. So this is 0. How much sine 0? Sine 0 is 0. If you forgot that, let's look at the sine graph. This is a sine graph. So it goes 0, pi, 2 pi. So you have to remember these things, okay? Because there are no excuses for this. This is a sine graph, that's a cosine graph. So you can see the value at 0 and pi are 0. So that means you get 0. So it is 0 plus c minus 0 plus c. You cancel each other, you end up getting 0. Okay, so wonderful. That's exactly what you expect. So when you integrate, you end up getting a 0. What does that mean? It is the algebraic area, not the actual area, the algebraic area. So if you know the actual area, what you want to do is you want to split the integral from 0 to the middle point, which is pi over 2 now. And then you're going to integrate from this to that, and you're going to kind of add the 2. Okay, so that means if you know the actual area, so area is actually what you can do is because by symmetry those two areas are the same, so you can say 2i is one area, so you're going to say 0 to pi over 2 only. Okay, only. So cosine x dx, we do the exact same thing here. Integral is sine x plus c, and then what you want to do, you're going to evaluate this at pi over 2 and subtract the value at 0. Actually there's a notation for that. What's the notation? You're going to draw a line and you're going to say you want to evaluate at the larger value and subtract the smaller value. That's what it means. So that means it's the same thing. You evaluate the value at the larger value first and subtract the value at the smaller value. So if you do that, it's the same thing. Sine pi over 2 plus c minus sine 0 plus c, and how much sine pi over 2? Sine pi over 2 is 1, so this is 1, and you can see the c and c get cancelled, so it's a 1, so it is 1. But remember one more thing, we forgot to multiply this one by 2, so we're going to multiply by this one by 2. Okay, so let's multiply this whole thing by 2. That's the number, so it's 2, so the area become 2 now. Okay, so that's the area. So area is exactly 2 for the cosine graph. If you get the area, if you need the actual area, area is 2, but if you just look at the integral, it is 0. So you can see that those two numbers are not exactly the same, so be careful. So if that means if you want to find the area, if you just integrate, you might not get the area. You want to make sure that when the function change the sign from positive to negative, you want to make sure that you're going to stop the value at the sign changes, and then you're gonna integrate one by one separately. Okay, so this is just a little bit too much, but we're gonna come back to this one in the next section. Okay, so but this is what I'm telling you is very easy to understand. So this is one of the big application of this different integrals. So again, so the different integral represent an area. Okay, different integral represent an area below a curve. Okay, area below a curve. Good. Now there are a few more questions also. So the question is, we just defined in the previous slide. So if I go back, in the previous slide we defined the definite integral as a limit. But remember, in Calc 1 we know that there are some limit they don't exist. Okay? There are some limit they don't exist. They goes to infinity, or sometimes get one positive values, negative values, different values. So in that case the limit doesn't exist. Even at infinity there are moments you cannot say the limit exists. So now there's a problem. So when the limit exists, okay, so if this limit exists, we call the function is integrable. Okay, if the limit exists, the function is integrable. So we're gonna say so if the limit, okay, that we discussed in the previous one, if the limit when n goes to infinity in the previous page, okay, if the limit when n goes to infinity exists, we say f is integrable. Say f is integrable. Okay, so if the limit exists, because it's not always the case, there are moments the limit doesn't exist. That may be a little too much when that can happen, but just remember that, you know, there are some situations when you take the right limit and left limit, you get two different answers. So there are things like that. So if that is the case, then the function is not integrable. But if the limit exists, you got to find a number, we say the function is integrable. And for us there is a result. So what the result says, this one. So it's actually a theorem. It is a useful theorem. So what it says, if the function is continuous, if f is continuous on AB, that's the interval we are talking about, on AB, or has only a finite number of jump discontinuities. Remember, what's a jump discontinuity? You know, if you have function, you get one value and it's going to jump to another value, so like that. So but it says that there are only finite number, okay, only a finite number of jump discontinuities, then f is integrable. Then f is integrable on AB. That is the limit, that is AB fx dx exists. Okay, because that's a good question, you know, whether, like, you know, we just say that, you know, it's the limit, but the question is, some of you may think about that, you know, or whether this limit exists always. Not really, you know, there are moments that this limit does not exist. Okay, so that's maybe too much for you, but if you take advanced mathematics, you know, advanced analysis classes, in those situations we can discuss some examples where what can go wrong. You know, there are some situations it's not gonna happen. Okay, so but for the moment, just remember that if the function is continuous or has only a finite number of jump discontinuities, then the function is integrable. Okay, integrable means a to b fx dx exists and it is equals to the limit that we just discussed at the beginning of the slide. Okay, so let's write it again, since this is where we write it. So we can write this as another theorem. So what the theorem says, if f is integrable, if f is integrable on AB, then the limit AB fx dx equal limit n goes to infinity, the Riemann sum I going from I going from 1 to, you can say, n, 1 to n f x I star. Star means what? Any point. Okay, you can be, it can be right hand point, it can be left hand point, it can be middle point, or any point inside the interval. And then the delta x, we assume that delta x is equal, but not necessarily. Okay, and where delta x equal b minus a over n. This is something you want to remember. And xi, okay, xi is simply a plus I many gaps, is also important. Okay, so this is the kind of idea behind, and this is useful. So I'm going to put a box in there. Good. So so let's look at an example. So how about this one? Express limit n goes to infinity, sigma I going from 1 to n, I going from 1 to n, xi 3 plus xi sine xi delta x as an integral on 0 to pi. Okay. So how do I this as an integral? So you know that. So what are the things that we need to understand? What are the limits? Okay, what is the starting value, what's the ending value? And if you look at this problem, you can see that it's very clear. Your starting value is a equals 0, and the ending value b equal pi. So that's the lower limit and the upper limit. You can write this one as an integral with the lower limit 0 and the upper limit pi. What else? And we know that the next part, so this is the function part, right? Function, you're gonna replace x by xi. That's what we did here. You see, you replace the x by xi. Now you're gonna go backward. Okay, so this is the function fxi. So that means you can replace this one by f. So that means your function becomes just x to the cube plus x sine x. Okay, just replace xi by x, and then delta x become dx. Okay, so it's very simple. So this is the integral representation of the Riemann sum. It's the integral representation of the Riemann sum. Okay, this is very clear. You can do 1,000 of them. Okay, you just need to figure out what is the lower limit and what is the upper limit, and then you want to figure out, you simply replace xi by x. Okay, so those are the things that you want to figure out. What's the lower limit, what's the upper limit, and you figure the function. In the function you replace xi by x, and then delta x simply replaced by dx. Okay, good. Okay, so it's easy, it's not that bad. Okay, so let's continue. So I just want to do like a one Riemann sum problem, just one problem, just to remember what we were doing before. So let's do this. So example, evaluate the Riemann sum. Okay, Riemann sum. Evaluate the Riemann sum for fx equal x cube minus 6x taking points at the let's say right endpoint, at the right end point, taking points at the right end point, and a equals 0, b equal 3, and n equal let's say 6. You will cut into 6 parts. Okay, so this is the kind of problem. So the answer, so we have a, which is 0, and then we have b, which is 3, and then you will cut into 6 parts. Okay, you're going to cut into 6 parts. Good. So what we have here, we have delta x, which is b minus a over n, so 3 minus 0 over n, which is 6, so you get 1/2. So delta x is 1/2. So let's try to calculate the numbers. Okay, so but you see that they say at the right endpoint, that means you're going to evaluate this value. So those are right endpoints. Okay, you need to know those numbers. Okay, what are these numbers? So what are those numbers? The first number I'm going to call x1, x2, x3, x4, x5, x6. Alright, x4, x5, and x6. So what are they? x1 is 0.5, x2 is 1.0, x3 is 1.5, x4 is 2.0, x5 is 2.5, and x6 is 3.0. Very good. Okay, so that means you need to evaluate the function at those points. So now the approximation. So the integral approximation by the formula. So what's going to happen? So that means your integral is going from what? 0 to 3 x3 minus 6x dx is approximately equal, because not equal, because not, we are not taking n to infinity, n is only 6, so approximately equal. So this is the Riemann sum, equal to the Riemann sum. Okay, Riemann sum with 6 points. This is called R6, just to mean that Riemann sum, but it is simply sigma I going from 1 to 6. There are 6 many parts, and f xi delta x. So let's plug in. So it is the function at the first point, which is 0.5 times delta x, plus the function at the second endpoint delta x, like that, and just put 3 dots, but you want to add all the points. And there was the last one, f 3.0 delta x. So you can see the delta x is common, so you can pull out that, so it is 1/2 in this case, and then you simply evaluate the function at each point. So if you do that, what do you get? If you want to get 6 numbers, so make sure that you use a calculator and get these numbers, because you know to do that in the exam. So you know, maybe like up to 2 decimal places. Okay, so if you do that, negative 2.87, and then you're gonna get negative 5 exactly, and negative 5.62, and then negative 4, and then 0.62 plus 9. So if you simplify, you end up getting negative 3.94. okay, so that's the approximate value of the integral. Okay, that's the approximate value of the integral. And you can see that so there's another way to find the actual value. So I'm going to give the actual value here, 0 to 3, 3. Oh, actually you can do this now, because we discussed how to do this and also how to evaluate these numbers. You find the value at 3 first and subtract the value at 0. So if we do that, we already know finding the antiderivative here, but don't worry about that, we can discuss that in the next one. Okay, so what is this definite integral means? It simply means the antiderivative. It's coming from, we can discuss in the next section. So if you find the actual antiderivative and plug in the values, you end up getting negative 27/4, which is exactly negative 6.75, and you can see that it is too far away from the actual value. Okay, it's too far away from the actual value. Because that happened because we only have 6 numbers here. Okay. So, but if you want to do that, there's a way. So you know that this is simply the limit. N goes to infinity. So let's write it. Sigma I going from 1 to n function. Okay. Now you can evaluate the function at the ith point. What is the ith point now? If you divide this into n many parts. So let's do the calculation here. So we start with 0, n with 3. We're going to cut this into n many parts. Okay, and then we also need to calculate the ith section. So what is delta x here? So delta x is 3 minus 0, you cut into n many parts. So the delta x is simply 3 over n. Alright, it's 3 over n. That's the delta x. What is the ith part? Ith part is simply the first number plus I many gaps. So that means, what's the first number? 0. That's the first starting value. This is a, so that's the a, plus I many delta x. So I times 3 over n. Okay, so in other words, 3i over n. 3i over n is the ith one. So what do you want to do? You want to evaluate the function of the ith one. So it is 3i over n. Alright, it's 3i over n. So and then what's the gap? Gap is simply delta x is simply 3 over n. So that is the actual general version of the Riemann sum. That's the general version, and then that's exactly equals to this one. So if you do this calculation, and you're gonna end up with that value negative 27/4, but we are not going to do that. But you can actually do it. We can use some notations there. There are some formulas for that, but we can skip that for this class. Okay. But if it is not online, I probably go over this full calculation. It probably take like 20 minutes to finish the whole calculation, because there are a lot of things that we need to discuss. But I'm just telling you how you can figure it out. Okay. Yeah, let's try to do but in the homework, what I'm asking you, I might asking you to write this version. I'm going to give the integral. Tell me what you get for the sum. Okay, so what I'm asking is simply this one. Okay, so this is what I'm asking. So write this version. Okay, so so that's about that. Good. So let's do more examples. Good. Yeah, how about this one? So let's see. Set up an expression for. So let's see. Set up an expression for 0 to 3 ex dx as a limit of sums. okay, as a limit of sum. That's exactly what I'm asking. What I'm asking is this one. What I'm asking is this one, okay, this one as a limit of sums. So let's do that. So what do you get? So the answer, we have fx. What is fx? Fx is ex. All right. And what is a equal? Okay, I'm going to replace this. Let's put 1 here. A equal 1, b equal 3, something like that. So what is delta x? Delta x is b minus a over n. 3 minus 1 over n. That means 2 over n. Okay, so it's 2 over n. So try to find the values. So we have x0, which is starting value, which is 1. We have x1, which is 1 plus 1 gap. So what is 1 gap? 2 over n. That's 1 gap. And then x2, 1 plus 2 gaps. So it's a 4 over n. So like that. What is xi? What is xi? 1 plus I many 2 over n gaps. So you can say 2i over n, right? So this is simply I times 2 over n. I times delta x. Okay, I times delta x. So that's what you get. Okay, so we have everything we need. Now let's write. So this 0 to 1 to 3, 1 to 3 ex dx, which is the limit n goes to infinity sigma I going from 1 to n. This is always the case, 1 to n, f x I delta x. I think we have everything we need. Just need to plug in limit n goes to infinity sigma I going from 1 to n, the function f. What are you going to do? xi is 1 plus 2i over n. Okay, 1 plus 2i over n. You see, that and that are the same. So that tells you a. That's the actually yeah. So no, don't do that because this is not exactly the case. But this is true. This is the a value. There's nothing to do with that. That's the a. Okay, that's it. It has nothing to do with I. Okay, I equal 1 is always the case. But this tells you what is the starting value. Okay, the starting value. And then you can add the 2 to get the ending value. So the b equal what? B equal 1 plus 2. See that value? So that's the gap. Okay, because that's the gap. So that's going to give you the ending value b. Okay, just add those two. This is going to give you the ending value. Good. And then delta x. Delta is 2 over n. Okay, that's delta x. Okay, so anything that does not depend on I, you can pull out from the summation sign. So that means you can simply write this one as limit n goes to infinity 2 over n. You can pull out the sigma I going from 1 to n f this part. Okay, so put it there, and that's the answer. So that's how you can write the integral as a summation. Summation. So but since you know the function at this time, you can write this one as limit n goes to infinity 2 over n sigma n I going from 1 to n. What's the function? Function is e. So it's e to the 1 plus 2i over n. So that is the final answer. Okay, that's the final answer. And later, you know, we can figure out how to actually calculate this one. There's a way to find this value, but that's we can do later. So we can use what we call the geometric series to find the actual value here, because this is going to be a geometric series now. Okay, so I'm going to show you some other simplifications if you want. So you can see that E is a constant, so you can pull it out. So you see this one you can write as limit n goes to infinity. You can put E, so it's a 2e over n, and then you have the sigma I going from 1 to n. So this is like a, when you multiply two powers, like we have e m n, this is e m n, right? So power for power, you multiply two powers. So that means you can write this one as, how we can write it, you can write this one as e to the 2 over n to the ith power. See that? So now these kind of things are what we call geometric series. Geometric series. Geometric series. We can discuss this in the last chapter. Okay. So for the homework, don't do that one. Okay. For the homework, just stop here. Okay. Just stop here. That's for the homework. Because what's going to happen if you try to simplify like that? The system might mark your answer as wrong, because the system can understand what you did, even though your answer is completely right. So for the homework right now, just stop here. Okay, just stop here. But later we're gonna continue that. You know, in the last chapter we can simply continue with that and actually find the exact value here. So there's a way to do this, because we have a formula for the geometric series. And from the geometric series formula, you can actually calculate that one, considering this as a geometric series. And then you can simplify this and get the final answer. Exactly. Okay. But if you know it, just go ahead and do it. Okay. So, if you want to do that completely, just studying a little bit, and then what you need to do is do it on a paper and send me an email. Okay, just attach it and send me an email. I'm gonna give you some extra credit for this homework, the homework on definite integral. Okay, so I'm gonna give you some extra credit if you try to completely finish that problem and get the final answer. But remember, you have to use geometric series there. Okay, this is like a challenge. Try this as a complete find the sum of this. It's using this method. Okay, find the sum and write on a paper and send me as an email. And if I get it, I'm gonna give you a few extra credit points added to the homework. Okay, so maybe 5 point, 10 point. Let's see. Okay, so yeah. So yeah, but I'm gonna give you time to time these kind of questions, you know, just to enjoy. You know, this is not just you do a few homework problems and be happy. That's not the case. There are a lot of things out there. So yeah, so if you feel like you want to do it, just go ahead and do it. I'm gonna give you a few extra credit points added to the homework. This is a challenge. Okay. So good. But you want to show the work, okay? You cannot just use a computer or something to find it and give me, okay? Because I know how to do it, okay? So I'm checking whether you can figure out what to do. But I'm also giving a hint. You have to use the geometric series here. Okay, so okay, that's about that. So there are a few other things that we need to do, because now we know that the definite integral represents the area below a curve. We're going to use that idea to do a few other examples. So let's see this one. Okay, so an example. So evaluate the integrals below. Let's do few below. by representing by interpreting that's not interpreting. Okay, so let's erase this. By interpreting each as an area. Okay, you understand the question? Evaluate the integral below by interpreting each as an area. So let's do this one. 0 to 1 minus x squared square root. What is this? What this says, find this integral. Okay, so actually to do this integral correctly, you want to wait for 2 more weeks. Okay, in 2 more weeks we can actually do this problem using what we call the trigonometric substitution. Okay, there's a special substitution called trigonometric substitution, and using that we can do this. But here we can just do this problem just by interpreting this as an area. Any ideas? So this is the y coordinate or the height, right? So the answer, so I'm going to do it here. Okay, so the answer, so y equal what? 1 minus x squared. If y equal 1 minus x squared, if you square both sides, you get y squared equal 1 minus x squared. That means x squared plus y squared equal 1. What does this mean? What does it mean? This means the circle. Alright, the circle with area with radius 1. So so that means, in other words, what we have here, that's the y. What we have here, what I'm asking, find the, see the y, this is the y, that's the y. Say, so that's the height, and this integral simply represent this area. Okay, so this area. So what do you want to do? Find this area. Okay, so so that means this is equal to the 1/4 of the area of the circle. Area of the circle. Why 1/4? This is only 1/4. It's going from 0 to 1. Okay, it's going from 0 to 1. So it's only 1/4 of that. So 1/4 pi. What's the radius? Radius is equal 1. Pi 1 squared, because the area of circle is pi r squared. That's the formula, pi r squared. So it is pi 1 squared. That means pi over 4. Okay, so it's simply pi over 4. Interesting. Okay, so so that means you can just integrate this. You can find integral just by interpreting this as an area, but this area is just simply the 1/4 of a circle. Okay, let's do another problem. How about this one? Let's say 0 to 3 x minus 1. What we have now, x minus 1. When you play, you know, this is a line, so, right? It's a line. We have y equal, so what we have here, we have y equal x minus 1. That's a y, the height. So this is a line. Okay, so draw this. So if you draw this, what do you get? So you plug in 0, you get -1. If you plug in 3, you get 2. So that's the line. Okay, so you try to find this area plus that area, but be careful, there's a positive area and a negative area. So you cancel. So there's a cancellation here. The height is 2. So this is 2. This gap is 1. This is 3, this is 1, so this gap is 2, this gap is 1. So I'm gonna call this area is A1, is called A2. Okay, so that means your integral is simply remember we discussed that if you have a negative height, those are negative areas, so that means your integral simply become A2 minus A1. Positive minus negative, always positive minus negative. I mean, not always, that's how we because what's gonna happen, positive gonna add, negative gonna subtract. So whenever you see a negative area, just subtract it. When you see a positive area, just add it. Okay, so I mean that's how you should remember. Okay, so let's do that. So so in this case, what are you gonna get? What's the positive area? 1/2 base times, it's a triangle. If a triangle, area is half BH, so right, base times height, base times height, that's the area of a triangle. So half, base is 2, the height is 2 minus half, base is 1, height is 1. We don't say -1 because we already put the negative sign. Okay, so how much you get? So you're gonna get 2 minus 1/2, which is 1.5. Okay, 1.5. That's the that's what you get for integral. Okay, so third one. Okay, I'm gonna give you this as a challenge. So see whether you can do this and send me in email. So these kind of questions I'm going to consider at the end of the course. Sometimes when you are in the boundary, like you are 0.5 away from 1 point away from that, I'm going to consider these kind of things. If you do this and send me, and if it is correct, I'm going to consider those things at those situations. Okay, so this is the problem. Do 0 to 3 like before, x minus 1 absolute value dx. Okay, so what do you get? Okay, again use geometry. Okay, so use geometry and try to look at the graph first, and then tell me what you get. Okay, good. So yeah, so this is a challenge. So I'm going to collect those challenges, and then but you need to send me before the next class. Okay, so send me before the next class. Send before the next class. Send before the next class. Okay. So yeah, so you can see that there are some problems that you can do using geometric representation, and you can completely ignore the calculator of the integral. So this is I mean I should say a shortcut. Okay, so you can consider this as a shortcut to do certain problems. Okay, so let's talk about some properties of the definite integral. Okay, so properties of definite integral. Good. So there are several interesting properties of a definite integral. So again, what's a definite integral? So when you have a to b fx dx, this is simply the area below a curve from a to b. So that's the representation. This area we can represent as the definite integral. Good. So what are the properties? So I'm going to go one. The first property is we have a to b fx dx, which is exactly equal to negative if you change the order b to a. So this will be very, very clear in the next section. Okay, when you talk about fundamental theory of calculus, this will be very, very clear. But for the moment, just remember that if you change the order, if you from A to B to B to A, it's going to change the sign. And since this is an area, if you go from A to A, what do you get? Do you get any area? You don't get any area, so it should be 0. Okay, A to A, any function, it should be 0. Number 3. So if you have a to B, a constant, just a constant. So so what do you get? If you have constant, so what's the area of this rectangle? This is C, A to B. So this gap times that, so it will be simply C times the gap is B minus C. Alright? For any C, it doesn't matter, it can be positive, negative, any C. Okay, number 4. If you have a sum, this is very, very useful. If you have fx plus gx, but we know that the integral is a limit, so that means all the limit property is going to carry over here. So that means you can split this A to B fx dx plus A to B gx dx. So if you have two integrals, you can integrate one by one. That's what it says. Very useful, even with the minus sign. Okay, so whatever the sign. Number 5. If you have a constant multiplying with the function, you can simply pull over the constant. So it is C A to B fx dx. Again, C is any constant. Is any constant. Number 6. Yeah, so this works for plus or minus. Okay, so it doesn't matter, but whatever the sign, just write the sign. And then we have something very interesting. This is also very, very useful in the future. So let's say you have a graph and then you have A, B, you pick something C. Actually C even can be outside, but just to remember this easily, we just put C inside. Okay, so that means if you have A to C fx dx plus C to B fx dx, this is equals to A to B fx dx. Okay, so that's obvious. So if you have one area here, the another area, you just add the two area, and that's the sum from A to B. So it's geometric representation is very, very clear. And then we have 7. So this is very, very useful. We can use that a lot. Use this a lot. So these 3 are very important, very, very important, and also this one. And then we have these 3. So if fx is greater than or equal 0, then the integral is also greater than or equal 0. Okay, and then if fx greater than or equal gx, then A to B fx dx is greater than or equal A to B gx dx. Again, for both of them, we assume that x is in between A and B. Okay. The last one, let's say if m, the function is in between these two values, the small m and big M. Then what happened? The integral is the smallest value of the integral is m times b minus a, the smallest value, and then the integral is in between a to b fx dx, the largest value b minus c. It's a kind of mean value theorem, you know. That's the mean value. So it's in between the smallest and the largest. Okay, and this can be any positive or negative value. So we don't know whether they are positive, negative, anything. It still works. Okay, so those are the properties of a definite integral. Okay, so fortunately, so it's in one slide, and try to go over these several times until it's like kind of clear. Okay, good. So let's try to do maybe one problem from this just to understand what's going on there, and that's the end of this section. So I'm going to do just one example just to tell you, like, you know, how to do things here. Good. Example, let's say if 0 to 10 fx dx equals 17 and 0 to 8 fx dx equal 12, find 8 to 10 fx dx. Okay, so the answer you know, we said that we said that 0 to 8 fx dx plus 0 to 8 to 10 fx dx equal what? If you go back, C number 6, A to C plus C to B equal A to B. So right, so we can use that. So A to B plus B to T, so this equals 0 to 10 fx dx. Okay, so according to this one, so this implies that 8 to 10 fx dx equal 0 to 10 fx dx minus minus what? 0 to 8 fx dx. So let's plug in. So 0 to 10 is 17, 0 to 8 is 12, so if you subtract you get 5. Okay, so things are easy, and also let's say find 2 times 0 to 8 fx dx. How about that? So this is simply 2 times 0 to 8. No, I want actually 8 to 0. That's what I need. 8 to 0. So, and this is 2 times. We know that if you switch, so it's become negative 0 to 8, right? If you have 8 to 0 and fx dx, so it's negative 2. 0 to 8 is 12, so that means negative 24. Okay, so you can do things like that. If you switch, you can change the sign. Okay, so that's pretty much what I want to do for definite integrals. And again, what we were studying, we have what we call a to b fx dx. That's what we call a definite integral. Definite means you have numbers. Okay? So we say that this is the area. Okay, area under the curve. What we mean by that? Okay, what we mean by that? When you have a curve, so if it is from A to B, so we have 2 areas, one is there, one is there. Area under the curve, when I say under, but be careful with that. So what you actually get is, if you call this is A1 and if you call this is A2, you actually get the algebraic sum of the areas. Algebraic sum, it is a plus a1 and a minus a2. That's the algebraic sum of the area. Okay, so you get the algebraic sum. Algebraic sum. Okay, so in the next section we actually learned that this differential integral is the antiderivative. Okay, that means you can use all those formulas to find this area. Okay, so I'm going to write this here. That's what we're going to learn in the next section. So we're going to learn that the definite integral is actually, it's not the definite integral, just an integral. Okay, but when you do definite, you're going to evaluate that. Definite integral is the antiderivative. Evaluate at the corners. Okay, the corners. Remember what we did? We calculate the farther corner, subtract the shorter corner. Okay, so yeah, so we can do that. That's the next one. So in the next section we are going to learn about that, and after that this thing's going to be much easier, because you can simply use the table to find those antiderivatives or the integrals. Okay, so things can be much easier after the introduction. This is just introduction, and after it's going to be very easy. Okay, so this is the end of the definite integrals. I know this is like a kind of long section, because you can see that there are a lot of things to discuss, but later this can be much easier, because after we kind of fully understand these ideas, we can kind of go much faster. So make sure that you can spend enough time to completely understand what we discuss here. Okay, it's very important. Okay, so thank you so much, and see you in the next section.